In section 6.4, we're going to be taking a look at factoring polynomials. And one of the new types of factoring we're going to see is factoring a perfect cubic function. So we do need to know some of the perfect cubes. So I've got those listed here, as well as a few quartics and quintics. Very few that you should have memorized. So for the perfect squares, I think I went up to 20, and I'll scroll this screen down in a minute. But for the perfect cubes, I would expect you to have them memorized up through 10. Perfect quartics, as you can see, just up through 5, as well as for the perfect quintics. And of course, any power of 10 you should know off the top of your head. So I would expect you to know all of the powers for 10. So scrolling down, looking at the perfect squares, I would expect you to have those memorized up through 20 squared. And then some of the other common ones, 25 squared, as well as any multiple of 10 squared. Because essentially looking at 30 squared, 3 squared is 9, double the zeros. So 60 squared, 6 squared is 36, double the zeros, so 3600. So I'd expect you to recognize those as well. All right, as I mentioned, we're going to be looking at how to factor a sum or difference of perfect cubes. So here is the formula. And trust me, once you actually start factoring the difference of cubes or the sum of cubes, the process, you'll get it memorized pretty quickly. It looks complicated here, but that's just because I have every piece of it laid out and labeled so you know what you're doing with it. So the first thing you do is you take the cube root of each term. Whatever symbol you have in your original question, you have that same sign in your first set of parentheses. So that's why it's the plus or minus, the same sign in both places. In the second one, we've got a squared minus or plus. So that is the opposite sign. AB plus b squared. It's always plus b squared because whether b is positive or negative, once we square it, it becomes positive. So again, this formula will become familiar to you as you practice it, and it is not as complicated as it looks once we see some examples, so don't get too scared by that. All right, so we're going to first start by checking to see if a given binomial is indeed a factor of a given polynomial. So our first example is x plus 1 a factor of x squared minus 3x plus 1? And lucky us, we can use synthetic division on this one because the lead coefficient of that binomial is 1. So that's what we are going to do, which is step 2 because we don't have a lead coefficient. So setting up our synthetic division, 1x squared minus 3x plus 1. Don't forget the asylum, so a negative 1 is what's going on the outside. Drop the 1, multiply, and add. This is not 0. This is step 3. If there's no remainder, it is a factor. If there is a remainder, it is not a factor. So the answer is no. All right, second example is 2x minus 4 a factor. Now in this case, normally we would have to do long division. However, that lead coefficient of 2 is a GCF, so we can factor that out. Now the binomial x minus 2 is in the form that we can use synthetic division with. So setting up our synthetic division, 2x to the 5th minus 4x to the 4th plus 0x cubed plus 2x squared minus 2x minus 4. Pulling the 2 out of the asylum, using our synthetic division. And this time when we did our synthetic division, the remainder is 0, which means x minus 2 or 2x minus 4 does go into that polynomial evenly. So yes, it is a factor.